are going to have a talk by Mr. Kishore Kumar Tatipalli. And Mr. Kishore Kumar have 20 plus years of experience in VLSI design, specialized on FPGA or ASIC domains. And he had done many end-to-end projects in FPGA domain and delivered multiple IPs to ASIC and having good exposure in emulation or prototype projects also. He have good experience in telecom product-based designs, and he has been working on 2G to 5G designs delivered to customers and successfully running on fields. He also working now on generative AI specific chip design domain, model creation, which will dramatically reduce the overall chip design cycle time and also provide quality designs. And currently he's working in Wipro, and we have a talk on generative AI for chip design. Now, over to you, sir.
My name is Kishore Kumar. I'll quickly cover VLSI services inside Wipro in 5-10 minutes, just as a marketing and what services we do, and then I'll go to the main topic. So our services starts from chip design, hardware, system engineering, and we have doing these VLSI services more than 30 plus years right now. And we have a current strength is almost 3,000 plus, 3475 is last year, but we have almost 3,200 right now. And we have expertise in technology wise 3 nanometer to 130 nanometer. We even have projects running at 2.5 nanometer also. So this is one of the largest company. We do end-to-end designs. We have done almost 250 plus designs tape out end-to-end from RTL to GDS2, and then on 500 plus system designs. And then we are working with a lot of top 3 chip marketing companies as well as many semiconductor companies. Almost whatever you take the companies like Google, Facebook, Amazon, Microchip, NXP, all the companies we have offshore development centers where we are working with various designs, maybe end-to-end turnkey or maybe IP designs. We have a foundries relationship also because we are doing an end-to-end relationship. We have collaboration with TSMC and Intel and UMC, Global Foundries and Samsung. Some of the sample success stories where end-to-end tape outs are done. One is hyperscaler chips and automotive MCUs and SerDes. IoT gateway and customer AVVR designs. I'll just cover the services what we offer in only main domains on the front end, like I will cover on the front end ASIC and then FPGA and then emulation and the DV. So this is the front end design services what we offer in the SoC architecture side. So we involve in from architecture to the GDS2 as I mentioned. So we involve with the architects on microarchitecture level, NOC designs, clock reset, power and DFT and DFX on the architecture level. And also on the subsystem, we involve in subsystem designs with the partitioning, once again clock reset and DFX and power structures. We have even IP designs where we start with the new IP designs coming from a requirement, or we have customizations which are coming from older designs, you portability point of view or changing any customizations, and we also have IP maintenance. Most of our projects running on IPs or subsystems. The end-to-end systems, end-to-end projects will be there, but there will be dedicated people. But most of our projects running on mainly on IP designs or system designs. Like 70% of our ASIC design engineers will be spending on IP designs or subsystem designs. And methodologies on the front end, we have Lint CDC, CLP, IPExact, MBIS, JTAG, whatever the new methodologies, what we have, the flows basically, these are running on the ASIC front end designs. Languages, Verilog, VHDL, system Verilog. The VHDL is very specific to RAID customers, but mostly we'll have Verilog and system Verilog. We used to have system Verilog mainly in verification, but now the designs are mainly migrating into system Verilog base because of the requirements and the features provided by the system Verilog. Design verification side, once again we have at IP level verification, unit level and subsystem level as well as a SOC level, which is full chip level. We do GLS support and the power aware verifications, formality checks, and then hardware software co-verification. And languages, once again we have SVUVM and SVOVM and customer specific languages, because there are some customers having their specific methodologies followed, so we even support that. But mainly all our verification targeted designs will have SVUVM. And languages, once again it's the same Verilog, system Verilog and C++. and we have system C for reference model generation in the verification. And scripting, scripting is dominating right now, Shell, Perl, Python. Python is becoming more dominant because automation is becoming more and more, and Python is the main language. So it's become mandatory for each and every engineer in our design to make sure the Python script certified. And environment developments, we have coverage driven, self-checking, automated, constraint driven, assertions. To reach the complexity of SOCs, to reach 100% coverages, we require complex verification methodologies and to reach different coverage levels. And sign-offs, we have coverage metrics and automotive specifications. So sign-offs and compliances, mostly we follow customer specific compliances. We do have our internal compliance checks, but we mainly follows with the customer and provide the guidance from the internal checklist, anything is missing in that. On the FPGA side, we involve in the FPGA design mostly end to end. We don't have specific designs targeted for FPGA IP specific. Generally, we get most of the FPGA projects from requirement spec to the validation on the board and deliver to the customer. And our involvement in the FPGAs starts with device selection. We work with the vendors and the customer choosing the devices, and then finalizing the pin list, working with the software hardware teams, power analysis, and the clock reset architecture, and the backend. And our designs of the FPGAs runs from low complex to high complex. We have designs done at 90% utilizations and frequencies running up to 500 MHz. And domain supported telecom, industrial, automotive, IoT, and security. Our major designs comes with the telecom and IoT specific, and some of them on the automotive. And IP designs, as I mentioned, very less it goes until unless it's done by the customer. Even we do support that IP designs targeted for FPGA, because IP design targeted for FPGA differs to the IP design targeted for ASIC. Some of the IP's designs may be common, which goes into ASIC as well as FPGA, but targeted FPGA designs always vary, because to meet the requirement of FPGA, their designs might vary. And the tools and methodologies, we support all the major FPGA vendors. We support AMD, Intel, all the Lattice, and Simplify, Spyglass, there are many more. These are the main vendor tools which we already have expertise in this. And devices, once again, all the latest devices, these are all the old slide basically, but we still support latest devices. Our team is also working some of the devices which are not in the market. Generally the FPGA designs where we work with the customers, the FPGAs are not in the market. The designs are ready when the FPGAs are ready in the market by end of next year. So I think we have almost 4 or 5 projects running in. The FPGAs are getting ready in the end of next year, even though we have started the designs. When the FPGAs are coming to the vendors, our designs will be ready. And once again, methodologies, we follow Scrum methodologies, checklist based, reviews, agile process, all those things are different methodologies. Once again, varies from project to project and customer to customer methodologies. Most of the projects run as agile methodologies, where our requirements are keep changing and customers prefer to use that. That's where the Scrum is coming into picture. And coming back to emulation capabilities, we support all major emulation vendors, Palladium, Velos, Jebu, and HAPS. The major emulation works, what we do is model builds. So model builds is nothing but you have a ASIC code or a subsystem or a complex IP, you have to convert and put into emulation build and then verify in the emulation platform. So we support in the architecture phase as well as hardware software validation. In the emulation, so basically we get model builds to be created, and we access mostly the platforms from the vendors. We don't have any in-house support of these platforms from the vendors. Because those are quite costly, they will be sitting at the customer locations. We will be using from remotely those LSF, using LSF connections and validate the platforms. And we use both an emulation as prototyping, because emulation is a pre-verification and prototyping is once again, you call it as pre-validation. So we have emulation side Jebu and Palladium projects mainly. On the prototyping side, we have mainly with HAPS. Yeah, and we also work with custom FPGA platforms, because a lot of customers still have their custom FPGA platform devices where the ASICs or the IP systems will be validated in their methodologies. Yeah, I think that's all I have on the capabilities point of view, what we do services at different levels. So our streams are basically split into ASIC designs, which works for IP or SOC level, and then FPGA team where it works for end-to-end or FPGA targeted, and we have a separate team called emulation. So these are the three major streams on the front-end designs where we support for ASIC and FPGAs. Yeah, so the topic I chosen is GenAI for chip design because GenAI is a buzzword you might know everywhere, everyone talks about GenAI. So at the same time, it is impacting a lot in the chip design. We see a paradigm shift in the chip design technology where the GenAI is coming into picture. And we expect in the next 3 to 4 years, this is going to take a massive change in the chip design. And the reason I took this topic because we see a lot of projects coming in asking for GenAI based conversions, or how much we can use the GenAI to leverage the productivity, or how much you can choose for quality point of view. So that's the reason, and even we have running 2 major customers running for creating these GenAI models, which are called the domain specific models. So you might heard a large language models, right? So we are trying to create with the vendors a new models which are useful for creating the chip design. It's not complete chip design, but we are going to help them how much they can reduce the cycle time, how much quality they can get building this new model. So the topics we can cover like what is the GenAI and how it is used in the chip design, what are the LLMs available in the market currently, and then out of the different use cases and the impact of the GenAI in the current market. As you can see, AML is not new. AML is there since many years, and the landscape looks like this. So GenAI is just part of it. As you know, AI is a computer system capable of performing some tasks. That's the AI which we already know. And ML is nothing but to do the computer system do the job. You need to train the system to learn from the data and take the decisions based on the data. And DL is the neural networks. Basically, DL mainly consists of the neural networks, how they are developed and how they are implemented, how they learn the data from the training. And GenAI is a subset of the DL. So every part is a subset of AI. So GenAI is not something new, it's already a subset of existing system. And GenAI is, the GenAI famous is because it generates the content such as text, images and codes and patterns. That's what it's called, especially called a generative AI. So to see the examples of GenAI, as I mentioned, AI is the simulation of human intelligence processed by computer systems, which we already know. Examples are like human robots and crop monitoring machines. These are part of the AI examples. And machine learning is a subset of AI, once again, that uses how the AI should work, the machines should work. It will create based on the algorithms and learn the data. So examples of ML are customer churn and credit card fraud detection and image classification. And DL, once again, it is part of the implementation of the neural networks, how the functions work, and based on and learn from the data how it looks like in the human brain. And examples of this DL is speech recognition and NLP processing for the characters and voice. And GenAI, there are many number of applications which you will generate the create text and voice chatbots and data augmentation systems. So what does the landscape look like on the silicon using this GenAI? You can see the GenAI market is rapidly changing. You can see cumulative annual growth rate is 36%, which is tremendous. Tremendous change from expectation of 24 to 32. You can see that almost 26 billion to 136 billion. There is a huge market impact coming with the GenAI. And where we see the GenAI market in the chip design is going to be predominantly on the logic design development, because we started designs writing codes in older days, and then slowly it is migrated into block diagramic based designs where IPs are provided by vendors, you club together and create the system. Now the system is going to change that. Generative AI is going to build your chips. Previously chips are designed for AI, chips are designed for DL, but the trend has changed. The GenAI is going to make the chips going forward. And on the segment of market, we see logic design is one of the predominant, and here I can see compared to design verification is dominating once again with respect to the physical design. So the area of, if you look at the complete chip design cycle, these are predominantly dominating factors in the logic design and power estimation and design verification. So what are the driving factors for this GenAI? One is the complexity. as the chip complexities are increasing, the size of the chips and complexity of the architectures, and obviously time for the development time has to be increased. That is one of the driving factor, and time to market. As you know, every ASIC design cycle, it takes almost close to 1.5 years, 1.5 to 2 years, but everyone don't want to wait until 2 years to come out of the chips. Everyone want to reduce their cycles. So that's where one of the driving factor for Gen AI. And design productivity and efficiency, as the designs are becoming complex, the productivity and quality has to be improved. This is one of the driving factor for Gen AI. And what are the restraining factors? Data availability. Still is the data is challenging to make the chips, because the availability of data is specific to could be customers, is not in everything is in open source, right? Like other software platforms. So data availability is one of the major concern, and computational resources. One of the major challenge with the computational resources is like number of GPUs, how to train the model. To get a large language model for a big number of parameters, it requires a weeks duration, minimum number of weeks. So that's where the factor coming into picture. And you can see the market of the chip design specifically, it's going around expectation on 2033 around 1713 millions. And you can see on the different models which uses by the LLM. I will in the next slide I will explain the different training methods also, which is GANs and autoencoder, reinforcement learning. These are the different learning processes by the AI. Okay, so where we see Gen AI use cases in the chip design cycle, complete chip design cycle? Is it only in the front end or some other places? So you can see first 3 phases are the front end phases, where you see the design specification, and then you verify the design verification, which is called DV, and then followed by the synthesis. So in these 3 front end designs, you can see where we can use the Gen AI. We can use for documentation, architecture understanding, because yes, you say complete designs of the architectures are trained, then the system can automatically give you what is the best architecture for your design. And then it can useful for RTL generation. Okay, you have a code, I can give you a description and it can generate a code. And then EDA scripts. So if you remember long back, we used to, if you want to write a script for synopsis synthesis or any compiler, I have to open a data sheet of the compiler script, understand the tickle commands or the GUI commands, and then write a script. So it takes a 1 week duration initially, very long back. But today, if we ask for a script with respect to the any device, it gives me in 5 minutes. So you can see the amount of drastic change where it can bring in the implementation point of view. And then coming back to the implementation point, like physical layout, physical verification, and power analysis. So in this section, they are looking at EDA script development, EDA helpful, how to make the placements better, how do we optimize the power. So these are the areas, some of the areas we see generative AI will be helpful. And then next into when it goes to the production, and also in the production you have a possibility of testing phase, possibility of introducing testing patterns and analyzing the data. So this is some of the areas we can see in the production field. And what is the level of customization is happening inside the different models. So most of the people in the LLMs are starting at these days, it's called prompt engineering, where you need to understand how to give the prompt to the user, prompt to the LLM to get a better output. Same prompt can give you a multiple different answers. So prompt engineering is nothing but how do you request the LLM to get your response properly. So that's where most of our engineers all need to understand how do you request LLMs. So that's a key part to use the LLM. And then called retrieval augmented generation. So this is the next level where you want to already have a LLM model. I want to customize the model with certain corpus data, amount of data, build a new model called a RAG. So I don't want to train my model. I have some amount of data which is already there. Suppose say I have hundreds of extra textbooks already there compared to what is trained by the model. So then that is implemented using an approach called RAG. I have a slide for that, I will show you details. And then next level is the instruction fine tuning. Okay, what is instruction fine tuning? I will specially make certain instructions to learn the model. So I will say that this is my code, this is my instruction, and this is my output. So that is basically set of instructions giving to the LLM to train the model. And then called fine tuning. Next level is a fine tuning, which is nothing but you are going to train the model with a huge amount of data. That's why it's a fine tuning. And then pre-training. Pre-training is nothing but completely building a new model with huge amount of data. So this is the level of complexity. When it goes up, it goes into the top level. So all the models today like ChatGPT or ChatGPT-4, Copilot, everything is called starting with a pre-trained model. So when any large language model, the name itself shows it's a large. When you say large, everything should be greater than at least 1 billion parameters, then it's called a large. So take an example of ChatGPT. Today, latest ChatGPTs consist of almost 165 billion parameters it's trained with. So when you think of that many parameters, when you think with respect to human brain, in generally they call it as human brain consists of 100 billion parameters of neurons. So that many, so you can say that today's LLMs are crossing the number of neurons which human intelligence can do. So that's the power of new LLMs what we have. So why Gen AI now? What is the reason of Gen AI? Because the availability of data, the different set of data is available, and the models are available which are vastly trained over the open source data what is currently available, and then patterns are available, waveforms are available to train the models so it can predict the data. So the good amount of data is available to build your new model. And the good amount of computational powers, many GPUs are coming with high computational power, we have access to cloud computing, because we can't buy a number of GPUs to train your model. So it has to be like paid wise or separately, you have to access that. And lot of open source software. So Hugging Face is one of the software developed from Microsoft, where you all have lot of APIs to train the model or to use the model, or you build the framework for the LLM. And some of the innovative DL models, so there are different model structures available for LLMs called generative adversarial networks, which is called a generative and discriminator concept, and transformers, they mostly use encoder and decoder concept, and reinforcement learning, which is nothing but with a human feedback the model is trained. Let's see how LLM works in general. So when we give a plain text of inputs, the model is trained with could be books, Wikipedia or cloud computing sources, any kind of things. The first thing is model is converted, the input prompts are converted into tokens, which is called a tokenizer. Tokenizer is converting that into your numbers, and that numbers will have forwarded to the token embeddings. Token embeddings nothing but each of your token or the word will have its own position inside the token, and that will be stored in a multi-dimensional arrays. And the token embedding will also have your specific unique position as well as its relative position, because it need to understand where the word coming from, what is my next word in your prompt. That is called a positional embedding. So once these embeddings are done, which are in the multi-dimensional vectors, then it goes through a process called contextual embeddings, which is nothing but the question need to be understand what is the context of the prompt, right? Otherwise it doesn't understand what is the context. So that is what called a contextual embeddings, where the weights are added to the corresponding basically to the existing tokens which are part created by the multiple dimension arrays. And then it goes to the feed forward neural network and automatically decodes based on the weights assigned to the neurons as well as the token embeddings, and then it decodes accordingly to the rest of the input what you requested. And then it estimate the, once it goes through the neural network and find out the solution, it also estimate the ranking. It gives a ranking of the probability based on the probability what is my best output receiving from the LLM. So that's where the general LLM works. So this is the RAG model example I am telling. So it's a simulation. You can see that he revised the code, he found out some problem, then I have a RAG database consist of, okay, I know what kind of RTL problems exist in the system. Could be syntax error or could be problematic rules, which are most frequently problems you can assume, that all can be filled with a RAG. So then it will react with a RAG response and then provide the feedback to the LLM, okay, this is the problem which I already know, please correct it. The LLM will get corrected and provide you the one more code, and then automatically compiler verifies that, and then the test will be passed. So it is basically building a framework. Lot of papers you see, they use the LLMs and build the frameworks, because It's easy to build, you don't need to build the model, you can use iterative way the LLM's responses and build a new and verify your methodologies. AI agents, so agents are nothing but they are doing some work for us. It's same way artificial agents, AI agents are basically nothing but they are executing our job. So you can see that an example here asking for look at the sky, will it rain today? If it rains, I require an umbrella. Something like that is a question, and the input need to be understood by the LLM, and he has to perceive that. He requests the LLM, and the LLM has to use some kind of memory which is understand what is the requirement, and then provide an action. Okay, today it rains, and here is your umbrella. So something like that. Agent is nothing but he is taking your task and executing it and giving you the result. So Alpha Designs is one of the company, is the world first company who started developing the AI agents for RTL code verification, debugging, design optimization. So these agents automatically take your input request and executes it. It's not just giving a result of is it working or not. They also correct your requirement and provide you the result. You can see here amount of models which are already available, not the LLMs. These are new models which are based on chip design specific. You can see on the top chip Nemo is from NVIDIA. NVIDIA is already claiming that they are using chip Nemo to build their to build their new chips. I will show you the chip Nemo slide also how they build the model. And you can see here platform and what is the task LLM is doing. You can see chip Nemo is doing with the interaction of the tools and building some of the applications. And what is the base model they started? You can see here it's a 70 billion parameter model, and training it's a PT and FT refer to the pre-trained model or a fine-tuned model, and then what is the number of samples, how much of data it is taken, how it is useful for, and the actions at the end is basically all the LLM models which are available in the market are not available to access. Like an example, chip Nemo is NVIDIA specific, I cannot access that, it's only useful to access to the NVIDIA team. Same like that, you have a models for Verilog RTL generation which are already there in the Hugging Face. You might know the Hugging Face is a data set where you can see all these kind of models available, data sets available, automation scripts available, frameworks are available. One of the biggest largest database which consists of all the models. And Dave is once again it's a Verilog generation. And then Verigen is also one of the Verilog generation code. RTL code and Verilog eval is two benchmarking methods. So you have designed a LLM, and how do you benchmark that, right? Your LLM is generating really what you expected. So that's why they have a benchmarking methods divided by different vendors. So what they will have is they will have certain golden designs. Say example of I have 1000 golden designs, and then I have 1000 test benches. I verify what is LLM generated output is accurate or not. Based on that, they will say that your LLM is giving this much results. The LLM's benchmarks are qualified using a pass-K factor. Pass-K factor is nothing but say I have 100 designs. I requested 100 designs. I have requested a prompt to the LLM. I get 100 designs from the LLM. Say first time out of 100, I may get 80 passed. So that gives a pass percentage called say 0.8. That is called pass K factor. The K factor also varies. Same 100 questions once again I give to the LLM, then he may give a different results. So when K equal to 2, the output response is better. So when the K increases, number of times you ask the prompt increases, same question, the pass percentage is always increases. And the requirement for LLMs is always the K should be lesser, your pass percentage should be higher. And today have not seen any single LLM is giving more than 60% for the medium complex designs. You can assume medium complex is nothing but not a processor design, it's simple state machines with some combination logic with running at something. So you can assume to reach the LLM to get a 95% of code quality design, it takes at least 4 years as per my understanding, because that is the level of data we have today. We cannot able to get a 100% code free generation from the existing LLMs. And auto chip RTL LM is also once again benchmark design. Better V is it a correction. Better V is nothing but you are getting a better auto generated code. That's a framework once again. RTL fixer, which I have already told. LLMs for security. So security retailer also I have seen lot of specific LLMs are built, frameworks are built. because security is a large area where you require side channel attacks are working, encryption, decryption, there are many algorithms. So, amount of data they trained on only security specific. So, these LLMs are targeted towards verifying your security based designs or to create a security based designs. Yeah, the last ones are, you can see the SCAR. SCAR is nothing but side channel attacks in the security where your data is taken over by someone else. And what is the potential usage in the different stages of the chip design? You can see system design, specification and architecture design. As I mentioned initially, documentation is always a tedious task. Can my LLM do documentation? If you can do documentation, it's 100% useful in writing the documents, right? So, largely reading the specifications and giving detailed structures, diagrams, understanding of the diagram. So, lot of places in the architecture phase these are used. If my architectures are trained also, like I have say I done 100 chips, I know the what kind of architecture needed for what level of design. If they are trained with understanding the architectures, my LLM can also give a better documentation. So, in our database we have LLM which also gives example. I give a specification document of RTL, like assume that it is a simple design, the automatically LLM gives me the complete structure. I get an RTL, I get a test bench, I get a document, I get even coverage support where you can write assertions. So, that is the way currently LLMs are built in. And then functional design and logic design, as I mentioned, RTL generation is always a key part. So, that is where all these chip chart or prompt auto chip is useful for the RTL generation. And RTL generation point of view, once again it is not only just generating the RTL based on my prompt, I also require to integrate my RTL. Like I have a subsystem with 100 files, I cannot do manually, because today every company has their own way of integration tools. Someone use IPXACT, someone use text file base, someone use CSV bell. So, we are also working towards customizing, and integration can be automatically done by the LLM. And bug detection, once again I have written a code, I want to fix that, I do not want to spend time. You give a bug free design to the LLM, LLM will give me the bug free design. I have a bugs inside design, pass it to the LLM, then it gives me a bug free design. So, bug free design also correction, it also useful in reviews also. Like I have a code, I want to review my code is following the coding guidelines or basic checks of the review. So, today in our project the customer is already inbuilt LLM which provides the review. So, if I run a Python script in my Visual Code Studio, I push into the Jenkins, I will surprise to see the next 15 minutes I get a feedback saying that this is my review. So, no one will review automatically, and the Jenkins integrated inbuilt will automatically giving me with a feedback from LLM. Okay, this is the code you have written in 100 lines, you can write this in 10 lines. So, you can assume that how much influence the LLMs can do. Physical implementation, once again back annotation and placement point of view, layout optimizations, LLMs are very useful. And logic synthesis and PPA, power performance area is one of the critical in any designs. So, this is one of the area we do not have much data in the internet, or we do not have much models. This is one of the area which going to be explored a lot, where everyone want to do their requirement to meet the PPA. So, there is a one paper you can explore, very PPA, which is explaining how you can reduce PPA based enhancement. And once again design testing and verification, like auto test bench generation, coverages you want to do, metrics you want to analyze, all those things will be part of the design testing and verification. This is ChipNemo I was talking about. ChipNemo is developed by NVIDIA for their internal development. So, what they have done is they have created trillions of data from the internet, open source, and created a pre-trained model, and from that they do training of domain specific training. So, they use complete architecture documents, internal IP databases, codes, script generations, everything will be trained. So, those are domain specific trainings, and that is almost close to 24 billions of tokens. Token is nothing but a word. So, when you say token, it could be a word or space, or it could be character. So, there are OpenAI is already available. You give a PDF to the tokenizer, it automatically tells you how much tokens you have. So, any large language model you want to train it, every data, at least the data should be in terms of billions. So, to get the billions of data, it has to be at least, if you just want to take an RTL alone, it has to be at least millions of lakhs of code. You can assume that how much data you need to train. And then it requires thousands of GPU hours. It's not like one day I get my training completed. It takes at least a week's duration to get the trained model. And once the trained model is done, they use the foundation model of ChipNemo trained with 128K chat instances. Chat instances are nothing but they already have known problems, known issues, suggestions from their chat history. So they use that data also, and then along with that they used 1.1K tasks. Tasks are specific instructions. Okay, this is my specific instruction to do this architecture. So they have a specific instruction for their databases. They are trained with that with some amount of GPU hours. That's where the model came out as called as a ChipNemo. And this ChipNemo model is used in script generation, EDA script generation, bug summary analysis, and the GPU architecture. The architecture side is quite complex, and that's why they are using this ChipNemo LLM to understand and give you the architecture study. I'm going to talk about little bit from the vendors, which already each vendor website you see, every place you see GenAI based tools. So that's where you can see here from Synopsys coming with Synopsys DCO, where the design space optimization coming in, where that's related to power and performance, and test space optimization, they call it as a TSO for the DFT testing and the testing side. And then verification side, they have many options: regressions, automatic test bencher, targeted simulations, AI input coverages, all these comes under DCO. And then analog space optimization you want to do in the analog area. So all the vendors are predominantly spending their effort building the AI driven tools. And this is from the Cadence. Cadence also coming with a AI platform, they call it a GDA platform. And then Cerebrus working on digital design side, improving the PPA and the productivity. As I mentioned, PPA is a large area where everyone wants to spend time. And then Virtual Studio, they is used for analog and custom designs, and VirtCM is used in debug and verification, and Allegro for the placement and the routing optimizations. You might know Allegro is a PCB layout design board. And then Optimality is a multi-physics which is used in DDR package optimization and die-to-die SI analysis, which are quite complex to analysis. That's why they are trying to use these LLMs. Okay, let's come back to chip design use cases. As I mentioned, the use cases in the chip design start from specification, where you want to drive your specification documents and understand the requirements. That's one area. And then the RTL, TB, EDA code generation. So this is predominant area. As I mentioned, someone wants to generate an RTL, someone wants to generate a test bench, someone wants to generate a EDA code for their designs. So one of the project where we are working on, this is predominant use case for the customer, where we are training the data at least with 100 billions of tokens. You can assume how much. So we have collected at least with open source, everything you call it from open course, or you call it from thousands of GitHubs, you call it from internal data. All these data is converted into tokens and trained to the model and to get a better accuracy. And how the RTL code generation comes accuracy, unless you train the model with accurate codes, you cannot get output also accurately. So there are a lot of pre-processing is required to train the models. Code reviews, as I mentioned, code review is one of the key area where everyone spends huge amount of time sitting together, review the code, find out the bugs. So why not use the GenAI, give you amount of, at least he can give you the automatic code review and provide you the feedback. And we also use this in code summary. People are very lazy to write in the RTL code lines, right? You have a code and someone wants to write comments in the code. AI is very useful in writing the comments. You can see a website called MG Verilog LLM. So what it does is, you give the code, it automatically writes the comments in the code. You don't need to write your own comments, because most of the cases legacy designs are the people who are developing, no one will verify this person has written a comments correctly. So we are going to use this comments approach also in our next generations, where we are going to build the new LLMs. Every file need to have a proper comments, so that it is easy for the next designer to understand the RTL easily. Engineering assistant is nothing but I have a spec. There are thousands of specs I have reading, so I have to collect the books, I have to search where it is, rather than if I train the model all these specifications, take a bus protocols, bus architectures, processor architectures, anything you train the model. So here also we see one of the customer we are training with almost close to 1000 books. Whatever the engineering is available, specifications, you call it as whatever, those models are trained, then I write in the prompt, automatically I get a suggestion. So people are trying to change their way of searching. People used to search in Google, we get a huge number of data, 10, 15 links. People are shifting using the Google to ChatGPT. Every mobile you have, people use ChatGPT. Every kids today use ChatGPT for their educations also. So the trend is changing. People are shifting towards using the LLM for the better prompt engineering, getting the consolidated result in a very quick manner. Assertions is one of the complex area in DV where you want to write because I need to understand the requirement, how do I write assertions, what is my requirement. Someone has to read the specification or understand the timing diagram or understand the flow diagram, then come up with an assertion. So to write an assertion, he has to spend complete requirement understanding. But today if I give a requirement of constraint requirement by a specification to the LLM will give you automatically assertions where you want to write. And then PPA, once again power performance optimization, where you want to meet your requirements basically, where how LLM can help in. Bug summary analysis, once again you have a bugs and give it to the LLM, it will automatically tell you what is the summary of an analysis. Once again documentation I already mentioned. Security compliance also one large area where people are looking to generate security related designs, also verify the security specific protocols. And debug is one of the large area once again in verification. You might know debugging the verification how tedious, so lot of EDA vendors and different frameworks are coming up. I pass the logs of the waveforms, I pass the files in the waveforms, files and the logs to the LLM. LLM will automatically come and debug and tell which line of code having a problem. So instead of manual intervention which takes huge, pulling out the lot of signals into the waveform and debug, today LLMs have a capability, automatically does and tell you where the problem is. So this is one of the use case which I told, very PPA. This is based on power aware requirement. You can say I have a requirement of my power required 0.1 watts and my area required this much amount and performance required to meet a 200 megahertz. So I got a code from LLM. First level is, this section is called a very rectify. Very rectify is nothing but I get a code LLM, I pass it to the tool, a tool says no, I have a problem, somewhere error, then pass feedback to the LLM saying that okay, this is the line having a code, can you correct it. So LLM should able to correct a large amount of places, then you get a better code. So this is nothing but building a framework, getting a optimized working code. Once the code is passed at the simulator level, next level is a PPA check. So how the PPA is worked? So they give they called as a PPA aware prompt. So we have to tell to LLM saying that I am getting my area or the performance, say pass it through the DC compiler or tool, say I get a 100 megahertz only coming from code, but my requirement say 125 megahertz. So we pass the LLM as a requirement and giving a prompt saying that, which is called a power aware prompt, saying that I have my frequency running at 100, but I need to meet this at 125, can you correct the design? They are able to correct it. How? The LLMs are trained with the PPS strategies called as a pipelining, retiming, clock gating or the parallel optimization. So what they do is they train the model with all these examples, because how the user implements, when something is not working, he has to find out what is the maximum path which is failing. Is that a combinational path? Can I introduce a pipelining, or can I do the parallel operations of my design or not? So all these methodologies, when you train the model, he understands the problem, he know where he can correct it. Of course, today may not be giving you accurate results. Going forward, LLMs are going to do powerful operations at the PPA meet. And this is one of the application in the verification. So assertions. So assertions, once again, you can use the LLMs to prompt saying that I want to write the assertion in this specification, this is my requirement. LLMs will give you snippet of the code and you can embed that code into your verification environment. And second thing is, you have a timing diagrams in your specifications. I have a timing diagram, I want to write assertion for that timing diagram. So, previously verification engineer need to understand the relationship between each signal in the timing diagram and write the assertions manually, which is the system Verilog assertion. Today, if you give the specific diagram to the LLM, LLM automatically writes the assertions. So, we are also internally doing one specific use case where the complete constraint generation including the assertions. When you take a SVUVM test bench, an example of this one, which consists of a top level module and it consists of a driver, monitor and sequence item and sequencer, and then the sequence where you want to drive to the DUT. So, this is basically SVUVM framework. In this, I want to constrain my APB sequence or the data which I am trying to drive towards the DUT. So, the LLMs can automatically generate the constraints towards the packet. Suppose I have an Ethernet packet, in the specific field I have to write only specific bytes, I do not want to write all the bytes, right, something like that constraint you have to tell. So, if your spec is having the details, today LLMs are able to generate a proper code of SV where you can automatically build. So, the same way, if LLM is able to generate a complete test bench, so we are working one more place where we are building an SVUVM test bench, complete test bench using LLM. Today you ask LLM an example of APB interface with an I2C controller, you got a design. Then you ask the same way, I want an APB controller with this my top design, I want to build a complete SVUVM test bench. So, LLMs are only good when you ask sequentially prompt, like you ask for test bench completely, he may not give you better. So, rather you ask sequential steps, okay, can you create an APB interface driver, can you create a sequence item, can you create a monitor, can you create a constraint for this interface, and then once all these components are built, then you ask, can you integrate all of them and give me a SVUVM test bench. Today they are able to do at least 80% for the medium complex design, the complete test bench is ready for you. Previously, lot of companies used to build a test bench framework. They used to have automation frameworks or some tools saying that because every new engineer cannot write scratch code developing a complete test bench. So, they used to develop models called different own Python script or automation script. You run the script, it will automatically create a template, either could be design template or automation verification template. But today you no need of use of any templates to create a test benches. LLMs are able to do whatever the type of format you want, they are able to generate the templates. It is not only template, they are giving you almost complete code for the medium complex designs. So, this is right side you can see one of the example where LLMs are generating automatically the constraints. The top one is a OpenTitan repository. OpenTitan has golden prompts and designs, consist of almost more than 200 plus designs. So, they are using those designs, providing the prompts to the LLMs and getting assertions generated, and those assertions are validated using tools and giving the feedback to the LLM saying that these assertions are not correct or not. So, basically trying to exercise creating the assertions inside the verification environment. So, as I told, benchmarking. So, these are the available benchmarking, maybe there are more, but I did not find more than this in the currently available. RTLLM is one of the benchmark which consists of 30 design examples. So, we can use this benchmark, one of the benchmark, and verify your LLM is giving. Suppose if you created a new model, you can use this verify and say my 30 design. The 30 design consists of various flavors, it may be simple, medium or complex. So, they have different flavors in that, it consists of combinational circuit or FSMs or different levels you have. This is very small, this is not sufficient for today's qualifying LLMs. So, this is what benchmarks are going to be enlarged in upcoming days. And next one is a Verilog eval, it consists of 156 proven designs, very small designs, AND gates, NAND gates and small FSMs and small DSP blocks, those kind of things, and they have manually written prompts and automated written, machine written prompts, they have both the types. So, they evaluate if a machine writes my prompt, how much LLMs can give you better result, if I manually write, how much LLMs are giving you. So, this is one of the benchmarkings. One more benchmarking, RTL repo is almost 4000 designs, they have a 4000 proven designs, you can use this RTL repo and verify your complex level, your LLM quality. And assert eval, as I told, you are implementing an assertions automatically from your tool. How do you validate those assertions are working? So you have already in a benchmark with the 20 proven designs automatically evaluating and give you a matrix. Okay, this much your LLM is working. As I mentioned, OpenTitan has large proven designs from the specific designs. It also has a security guidelines which you can use for verifying the security related topics. On related to this, what we are trying to do is we are coming up with a standard benchmark. We are going to use all these, along with we are going to develop at least 500 plus designs to create a new benchmark. So that is one of the area where we are working in, because today LLMs are these are quite medium complex or low complex. There is nothing having a complex design which can validate today LLMs is generating proper code. Okay, so what is the training process? So if I want to build a new LLM, right, what is the training process? So first we understand the basic, what is your requirement to build a new model? Do you really need a model, or you want to use a model, or you want to build a RAG model? So on step 2, you have to prepare the data. It's not just a collection of data. Collection of data cannot be useful until you process it, because in the open source you get millions of data, but if you train directly the data, your LLM output accuracy levels will be drastically low. Until unless you process the data, make sure that what you train the data is accurate, then only it will be useful. So that's all the data preparation and processing comes into picture. And then next, model and architecture too, because there are different models. Most of the dominant model is transformer architecture model. Most of the LLMs are using this one, and if you are especially for image processing and video processing, they use the GANs, which is the generative and discriminator model. And once all these things are done, then the step 4 is fine tuning. So fine tuning, there are a lot of OpenAIs are available. You can use from Microsoft Hugging Face library set to tune the model, and you can create a new model. And then once again the model is created, then you evaluate the model, is the model performance is expected or not. So these are the detailed steps. Once again from the previous slide, you have to define the goal, what you want to do, and then pre-process the data, like you have to tokenize the input, understand how many tokens you have, and does it sufficient to train the model. Suppose say if I am training a model with existing Llama or Copilot or ChatGPT, which is already having say 100 billion parameters. If I train that model less than 1 billion, it is not called a training. So I should have good amount of training data, and that should be pre-processed with the quantifying the data, then only it will be useful for training. And pre-processing is the once again the preparing the data, process it and make it ready. And model selection. So you have to choose the model, what type of network architecture you want, what is the model, transformer or GAN, and define the parameters, number of layers in the neurons you want, how many layers you will be using, attention heads, what is the weights you want to do in the between the neurons, and different hyperparameters are nothing but how much time you want to train, how much iteratively you want to train, it's a complete epoch or only certain parameters. So those are comes under hyperparameter, and then the framework. So what is the framework? Because to train the model there are multiple frameworks available. TensorFlow, PyTorch, these are the two famous models, and completely open source. There is nothing you need to buy it, everything is available to build the models. And then initialize the weights according to whatever your input requirement. And DeepSeed is a machine learning optimization library, once again developed by Microsoft. This is the command which is used to train the model. And training, once the model, all the configurations are selected, you will be training the model which is required by, which is in terms of millions and billions of times. And this model training generally takes at least 2 to 3 weeks. It depends upon the amount of size. So, yeah, and it requires at least 7 to 8 GPU cores. It's quite complex, and you have to wait the result until it gets a new model. And fine tuning, once you create the model, once the training is done, evaluate the model and verify the performance. These are the different training methods. So pre-training is nothing but you are training completely with raw data, which is completely vast amount of text data. And then fine tuning is nothing but you are supervising the training, means I have specific instruction and specific labels. This is my say example from the Verilog point of view. I can say I have a description of my requirement, I have a code, I have a description code, something like that. It's a supervised training, that's called a supervised training. Or it could be instruction based, like say I have true or false conditions for certain amount of data. And then reinforcement learning, it is nothing but you train the model, get the feedback from the human, and then once again give the feedback to the model. Parameter efficient tuning, which is one more tuning method where they only tune certain amount of parameters inside the model. These are very useful for certain amount of domains like medical diagnostics and fraud detection. They have huge only specific data will be trained and in that area. So what are the challenges in the Gen AI? The challenges are obviously complexity and scale. The model complexity is increasing today and the data is a challenge. And compute, once again you require a huge amount of GPUs to train the models. With a single GPU you cannot train a model. If you want to use 1 or 2 GPUs max, you can train a model close to 6 billion parameter model, something like that. And data availability, today's every vendor will have their own data in their customer databases. No one wants to release the data. So data availability is still a challenging, even though its vast amount of data is available. And integrating into existing environment, this data availability to integrate also is a challenge. Suppose if I build a model of LLM also, how difficult to integrate it into your existing environment. Physical design, there is a challenges in the physical design aspect, how we can meet the physical design challenges. Energy consumption, as we are using huge amount of consumption with the GPUs, I saw some place the energy consumption, like it will be doubled in 2 years what we have in today, the amount of GPUs consumed. And also if you want to generate a good amount of quality picture, it takes the energy is equivalent to one single full charge of your mobile. You can assume how much amount of energy we are going to consume with the LLMs. Accuracy is once again critical, where you get a code, but you get a code or whatever your task, but accuracy is always a concern. And security risk, today this is a major concern in the LLMs. As the data is spread, everything is becoming open source, security is becoming a complexity, all IPs can be spread, where the data is going we don't know, people are using their customization, people are really following the security rules or not, that's a challenge. You could have seen in recently I saw someone is using a musician lyrics and quoting that this is my lyric. So that's kind of examples we have a security risk. In the IPs also it becomes the same. You can get a lot of vendor codes today available without any security aspects. So what is the impact with the generative AI into the market? The impact, as we discussed, like we can do automatic design and optimization, we can increase the verification capability where we can build test benches, lot of assertion capabilities or coverage driven, lot of things in the verification area we can use. And generative physical design is one of the area you can use it for generative AI. And layout design, DFM, design for manufacturing, you have lot of design methodologies really required to have a manufacturing side. And AI driven and testing, because a DFT case or ATPG cases, lot of patterns are required, you need to learn the data. So all those things is one of the use case. And then manufacturing data analysis. Okay, and then coming back to the last slide, maybe Wipro AI 360 platform. This is the platform where we have, it's a framework basically. The services it will provide, the AI 360 is nothing but it is developed internally by Wipro, which consists of, you can select lot number of models, what is available in the latest market, and also build your framework. Say I want to build my examples what I told previously, RTL fixer or very PPA, all those kind of examples you can build using this framework. This framework is available such a way that you can, this is once again internal, you can suppose say I have a text document, I pass it to the text document, or state missions, I have a state mission, I can import to the tool and automatically I get a code. So if you, this is mainly useful for the development mode, it's not just like a prompt engineering. And these are the different services with the AI 360 platform, applied AI services which is used in predictive analysis, data science, ML platform, and towards the intelligence, marketing, supply chain, many cases. So we have almost, as I know, we have 500 plus applications are already delivered to the customers using this platform. and Wipro is spending good amount of investment. You can see the 1 billion investment just on the A360 platform. And today for all our engineers, generative AI is a mandatory training and they should be level 2 certified, just not just understanding at the level. They have to be level 2 certified, every engineer, with understanding of development mode.
Any questions?
Sir, I don't know much about the models. But
Even I am learning.
no, I heard let us say A, B, C, there are models.
Yeah.
So at which level, which models are more accurate? That I am missing in your presentation.
So that's what I am telling. It depends on accuracy comes. What is your domain you are looking at? Are you looking at chip design? Are you looking at?
No, I am talking about the chip design only. In chip design at various levels, like RTL level, then verification level, then DFT level, then physical level.
Yeah.
So all at various levels.
So,
what I'm missing in the presentation is so far like benchmark models, more accurate models.
So
that information, if you could
today,
able to provide.
Today, if you ask me, there are no LLM model really for chip design giving a better accuracy. What I see analysis from the different models, what we exercise, ChatGPT 4 is giving the best results, which is giving at least.
No, I'm not talking about such. Models like.
You are asking a model, or you are asking
to train we use models, right?
Yes.
Them I am asking. It's a ChatGPT is a LLM.
Yes.
So some other models that we train them. No, we import some models in TensorFlow and then we train that model.
That model is only base model. That's a pre-trained model. The pre-trained model you are talking in the TensorFlow or whatever, right? You will be checking a base model, right? The base model is nothing but the baseline model what you are choosing. You may be choosing LLM, Llama, or you may be choosing Copilot. There are a lot of amount of models available. That's a baseline model you are choosing. Suppose I am building a domain specific model for chip design. Example I am talking. So I can take Llama 16B and I can train the model, and my new model may be called as a chip design specific, whatever name you put it. But the baseline model always, how do you choose the baseline model? Maybe that's your question.
Yes,
I don't
yes.
know.
Yes,
How do you choose the baseline model? Yes. So the baseline model is currently chosen mostly based on latest available models, not the model which is available at least 1 year before. Okay. We at least see, we have tried at least 3 models. One is called a DeepSeek, which is based on IBM, that is giving little better result. And then we used another one called GPT, which is inbuilt once again. So today there is no accuracy model you can choose it, because we are creating a new models, right? So the domain specific models, when you are creating, it's okay to choose any model which is latest in the market. It depends on the size of the model what you want to choose. If you want to choose GPT, is a quite huge database. Why don't you want to go to GPT if you are looking for only specific area? I can choose a small model, say a DeepSeek is example I am telling you, which is comes at just a 16 billion parameter, very small size. You can choose in 1 GPU card, not 1, 2 GPU cards maximum. You can train the model, get an accuracy. So we train this DeepSeek model with RTL examples, what we tried actually I am telling you, and we get a accuracy of 70%. The model is same, the accuracy of this model is an equivalent to GPT-4, which is almost 10 times. So you have to choose, is a domain specific model what you are choosing, how much is the parameters what you want to train, how much is the GPU's capability what you have, what is the accuracy level you are expecting. These are the different parameters of the chosen models.
Another question is we trained, first we train, then later is the inference.
Yeah.
So during training, there may be lot many parameters that gets changed. So in case I heard like a hardware, on hardware itself they train the model. So how is that possible? Because when hardware is something that is fixed, it depending upon the bias values, depending upon the weights, then we supposed to have the hardware requirement. But how is that possible in such scenario to train the model on a hardware?
Because we are using GPUs, the algorithm, we are developing the algorithm to train the models, right? Suppose you have a model, you need to find out amount of hardware what you required. See, in FPGA you are building, you are using FPGA, right? You are developing an application and you are running the model inside it. Like, have you seen example of forget the GI?
Sorry to interrupt. My point is, while we train the model, to, in case if we are not getting the accuracy, it is yet to require, a lot of iterations get the perfection there. Um, I heard that on hardware itself, training is possible. On hardware, training is possible. So how is that possible training? Because in hardware, when we talk about the hardware training, on hardware, the hardware is anyway fixed.
Hardware is, we are not changing anything in the hardware. You are running the algorithms in the hardware to get the model. Like an example, you take an FPGA, that's what I am telling you. You are building an application, right? FPGA is fixed. I am building my own application to run into the FPGA. It's same like that. You are using the GPUs to build the model using the GPUs or using the CPUs. It's nothing but you are training data, right? You are not changing anything in the hardware. You are creating, using the GPUs, you are creating a model. You are not touching the hardware.
Okay. Okay. Thank you.
Sir, a small correction I wanted to say, the transformer architecture that you discussed,
Yeah.
in that there are two embeddings. One is positional embedding and another is contextual embedding.
Yeah.
So what you told, that addition of the position and the
Context
input
embedding.
embeddings,
Yeah.
that is actually not context embeddings. Context embedding is attention mechanism. What
Yes.
you told is positional embedding. So positional embedding will add
Positional
that is
embedding
not
is the
sent
first
to the that is not sent to the neural network. Then it goes to something called attention mechanism.
Yes.
అక్కడ key query value vectors అని మూడు తయారవుతాయి. So basically what is the output of contextual mechanism is, suppose if I have a word which says Hyderabad is the best city in the world. So Hyderabad and city ki there is a huge correlation.
Yes.
But as words like is, the ki పెద్దగా లేదు. So what happens is we get something called attention weights. These are softmax outputs.
Yeah.
So the attention weights will be high for the word called city because it is correlating with Hyderabad.
Yeah.
So then we get a weighted average of the entire embeddings.
Yes.
So basically our output embedding will be having the context information also. That is happening in the contextual embeddings. That goes to the neural network, not the positional embedding directly.
Yeah, I have not gone inside it because we generally use APIs and not spend insight to what is happening. So.
Okay, sir. Okay.
So when you say LLMs can be used to generate RTL codes and test benches, what exactly will be the input to them?
Prompt or your spec. Say I asking, can you generate, you are a Verilog expert, please generate my code with an I2C interface with APB, I2C controller with APP is one of the prompt. But even I can pass a document giving a functional description of the requirement along with the timing diagrams, maybe pictures, everything. You can give a requirement spec or a prompt is an LLM input.
If two people are using the same LLM and giving the same specification, the output would be same.
Most probably that's expected the LLM behavior, but it will not be same. You may see a variation, minor variation. The minor variation comes maybe for medium complex design. For low designs you may not see a variation. You will see almost same. But when you go to the complex designs, you may see a difference. That's the future of requirement of LLMs, where it has to be enhanced in such a way that LLMs should give you accuracy of the designs.
Okay, thank you.
Thank you, Kishore sir, for sharing your knowledge with all our participants. Thank you very much. Now, may I request our beloved head of the department, Professor Ramakrishna sir, to felicitate our guest.